So for position vectors are always thinking about starting at your origin. So we use O for our origin. If you had the point 4, 2 as your point P, then your position vector would be 4, 2. So it just gives us some sort of reference. And since your origin is a fixed point, this is not a vector that is just anywhere. It has a specific starting point and a specific ending point. So we usually denote it with just the vector P or with whatever letter you're using. So position vector for OR, if your point was R, would be little case r. So if you have 2 points, M and N, so here's our point M, and here's our point N, you would have position vectors M and position vectors N. Then if you wanted to say, what does the vector Mn look like? Well, in order to go from M to N, which is this resultant vector here, using my position vectors, I would have to first start at M and go to O, and then go from O and go to N. So if we wrote that out, M to O would be negative M, negative the position vector, because you're going in the opposite direction. And then O to N would just be that position vector N. Oh, it spells the word moon. That's so cool. And you'll see a lot of textbooks end up writing this like this, because it looks nicer to subtract. But I prefer writing it as negative M plus N because I really can see it from the picture. I want to go from M to N. That means I have to start here, go negative M, and then go positive N to get there. It's not as visually easy to see going positive N first and then negative M. Same thing if you went from N to M. Well, you would first go from N to O, and then O to M. This would be negative N plus M. Now, if P is halfway between M and N, so if we go back to our diagram here, and we put a point P halfway, does it make sense that the vector from M to P, right, OP, okay, sorry, we want to find this position vector O to P. Does it make sense that M to P, well, that's not a P, M to P is equal to half of M to N? So if you wanted to do half of M to N, what you could do is just take what we found as M to N, which was minus N minus M, or minus M plus N, and just do half of that. So what will that look like? Well, here. If I want to go from O to P, I could first go from O to M, and then go half the distance from M to N. So I'll draw that out again. here's O, here's M, here's N, halfway in between was P. So I want to go here to here as my resultant. I could do that by going from O to M first and then halfway from M to N. So what does that look like in terms of M and N? Well, O to M is just our vector M. And we already figured out that M to N was negative M plus N. If we distribute the 1/2 to each of those vectors, M minus a half M will be half M plus half N. So what this means, 1/2 M plus 1/2 N, as far as our diagram goes, take out a different color, purple. I'm going to go halfway from O to M, and then the same direction, here's O to N. If I go in that same direction, O to N halfway, if I take that and match it up to the tail there, you see you end right at the point P. What happened to this other M here? Well, these M plus a half of a negative M would be like M minus a half M. Think of those sort of like terms because they're vectors. You've gone M this way and then negative M back this way would end up right there, which is the same as just going half M to begin with. So here's our next diagram with a bunch of midpoints. We have 3 position vectors A, B, and C. We want to find the position vector from O to P and the position vector from O to Q. So looking at our diagram, how can we get from O to P? We can get from O to P by going from O to A and then halfway from A to B. Well, O to A is already one of our position vectors. But A to B, if we want to figure out what A to B is, well, we can go from A to B by going backwards on A, back to the origin, and then along B. And we get a similar result to what we had before. It's just half towards A plus half towards B. Now for position vector OQ, it's going to be the same idea. We can get from O to Q by going from O to B and then going halfway from B to C. O to B is position vector B. To go from B to C, you would have to go back to the origin and then along C. So we'll get half B plus half c. So now in question B, we're going to find PQ in terms of A, B, and C. So what we're trying to find is you want to go from P to Q in the most efficient way possible, but you're told you're only allowed to walk in these directions, either forwards or backwards. How would you go about doing that? Okay? So this is what question B is asking. You want to go from P to Q, but you're only allowed to walk in the direction of the purple lines. And you want to do it in the most efficient way possible. You can only walk, let's say the idea is this. You can only walk in the direction A once. So you have to decide how far you're going to walk in that direction. And then once you've decided to stop, then you can only walk in the direction B once. Figure out how far you're going to walk. And then in the direction of C only once. Maybe you don't even need to use one of those. We're going to find out. Well, as far as the pictures that I have here, I have the three purple lines, and we already figured out this line and this line, those position vectors in part A. So as far as going from P to Q, using the lines that I have are given to me, I can do that by just going backwards on P and then forwards on Q. So P to Q is just going from P to O and then going from O to Q. And this will be negative O to P, and we figured out O to P already was 1/2 A plus 1/2 B. And O to Q was 1/2 B plus 1/2 C. Putting these all together will give us negative 1/2 A plus 1/2 C. So now going back to our diagram to see what does this mean. I'm going to erase all of this stuff. I'm going to measure negative 1/2 A by starting here and drawing that blue vector. Does that look like negative 1/2 A? And 1/2 C, I'll draw in green. I'll start here and go there. Apparently, if I start at P and go negative 1/2 A, and then where I end up, go 1/2 C, I should end at Q. And sure enough, it matches up pretty much perfectly. So if you were told you were only allowed to walk in those three directions, that would be the most efficient way to do it. So here we have a hexagon. Some things about regular hexagons is that if you drew all of these lines to your center, you would make a bunch of equilateral triangles. And does it make sense that this line, this line, this line, and this line would all be parallel? And this one, and this one, and this one, and this one would all be parallel? And these ones are really probably the easiest to see that they would all be parallel. So we've got a couple of vectors. We're told that from O to A, is equal to A, and from A to B is equal to B. How could we go from O to B using those paths? Well, this one is quite easy to see that you would, if you'd started at O and you went along A, and then you went along B, you would get from O to B. Part B says, what would it look like to go from B to D? So now I'm interested in going here down to there. Now there's a number of different paths you could choose. Okay? You could choose this purple path. Can you see that you could go negative B, negative A once, negative A again? Does that make sense as a way to go from B to D? So writing that out, the purple path would be negative B once plus negative A twice, which would be the same as writing negative B minus 2A. Maybe you thought of going from B to C first, and because that's the same direction, can you see that that's negative A? And then going from C to D, which is the same as negative OB, which we figured out to start with. And if you added those together, again, you'd get negative 2A minus B. So depending on which pathways you decide to use would be how you'd set this up. But either way, you'd get that as your answer. Finally, part C says try to find C to F. So now we're looking, how can we go from here to here? Well, maybe you say, I want to go from C to B, from B to A, and from A to F. Can you see that C to B is the same as the vector A? From B to A, that would be negative B. And A to F is the same as negative A plus B, which we figured out in part A. If you put all those together, that green route would be negative 2B. Can you see a more efficient route? Yeah. The more efficient route is just along the red to begin with, because you know that this is parallel to negative B, and that one would be another negative B. That would be a more efficient route. You still end up at the same place, and when you simplify it, you still end with the same answer. Now these first three examples, we've dealt with a couple midpoints. We've dealt with parallel lines. In this last example here, now we can start dealing with a couple of ratios. So we've got a parallelogram, and we're told that there's a point P lying on extended so that the ratio of AB to BP is 2 to 1. So that means if this is 2, this is 1. And the ratio of CQ to QB is 1 to 3. So that means if this is 1, this is 3. With those ratios, where that's going to come in handy is to see, can you see that going from the vector A to B is the same as going 2/3 of the way from A to P? So even though the ratio there is given as a 2 to 1, when we look at how does that work with fractions, that gives us a fraction of 2/3. And the same thing, going from C to Q is 1/4 of the way from C to B. Now with that in mind, I want you to try those 4 there. And then those 4 questions in part A, and then try part B as well. So from A to B, the first part, that's pretty straightforward, because if you're starting at A and you want to get to B, you can do that by going negative A plus B, and sure enough, you end up at B. Now from going to A to P, sort of 2 different ways you can look at that. You've already figured out A to B. You already know what this is. Going from A to P is in the same direction, it's just longer. How much longer is it? Because this length was 2 and this length was 1, does it make sense that this new line is 1.5 times longer? Or if you add this all up, the total length is 3 over the 2. 3 over 2 is the same as 1.5. So that's one way that you could look at doing that, is say it's 1.5 times longer, so all I need to do is multiply AB by 3 over 2 and get my answer. Another way, if you're like, oh, that 1.5, it doesn't come naturally for me to see that A to P is 1.5, well, you could go from A to B and then say, well, what do I need to go from B to P? Well, that's half of that length. So if I go A to B and then add another half A to B, that will also get me from A to P. So if that is easier for you to see, then you could use that as well. Either way, when you simplify it, you'll get negative 3/2 A plus 3/2 B when you solve it. The third part, now finding O to P, I could go from O to A, since I know that, and since I just figured out A to P, if I go from O to A and then A to P, that'll be the same as going from O to P. So now I've found my position vector for P. And simplifying that, I'll get negative 1/2 A plus 3/2 B. Look at that, forgot some arrowheads. And finally, for finding O to Q, if we go back to our diagram, I want to get from O to Q. O to C, since this is a parallelogram, will be the same as A to B. And C to Q is just a shortened version of O to A. And if we think about how much shorter that is, that's going to be 1/4, since the ratio is 1 to 3, the whole length is 4, and going from C to Q will just be 1/4 of the vector A. So putting that together, oh, I wrote it different here. Okay, I'll show you this one. What I've got here, another way of doing it is thinking of going from O to B first, and then going backwards, and now this would be 3/4 of vector A. So either way, you could use the green route. The green route would be going from A to B, and then going 1/4 of the way along A, or the blue route, going from O to B, and then backwards along A. Either way, when you simplify it, you'll get O to Q is B minus 3/4 A. And now that you've got position vectors for P and position vectors for Q, you can find out P to Q. So erasing this right now, we want to find out what is P to Q or sorry, Q to P, not P to Q. The arrowhead, Q to P. Well, that would just be going from Q back to O, or negative OQ, plus OP, simplifying this all together, and we get 1/4 A plus 1/2 B. So what does that look like? That means if I go 1/4 of the way along A, which I know goes from O to Q, and halfway along B, which is right there, if I put those together, it matches up as going from Q to P. Which I think is kind of cool that you could figure out how to go in a length that really looks quite differently than the vectors that you started with, but you can find out how to go just certain proportions along those lengths to find your answer. Go back to this one. So we've got, in 3 dimensions, 3 position vectors of points A, B, and C. And we want to show that all 3 of these points, A, B, and C, happen to be perfectly on a straight line. So there's 2 different ways, theoretically, that we can go about this. One, we could say if they're in a straight line, then the distance from A to B, call that x, and the distance from B to C, call that y, that has to equal the distance from A to C, needs to be x plus y. Because if they weren't in a straight line, can you see that it would be much longer to go from A to B and B to C than it would be to go directly from A to C? But if they are in a straight line, then that distance needs to be the same. Okay? So that's one way that we could look at this. If this was in 2 dimensions, and we're going to do this idea the same way in 3 dimensions, another way that we could think about showing that these are in a straight line is if the slope the slope of A to B, which is m, if that's the same as the slope from B to C, then you're going in the same direction. You haven't changed directions whatsoever. And then you would find out that these are in a straight line. Those are two concepts to approach this problem. We're going to see that the mathematics of doing the slope part is going to be less work than the mathematics of finding the distances. But again, you have to say to yourself, what would I think of? And whatever method you come up with as a way to solve this, then chances are you'd probably work through that. And that would probably be the quickest way for you. So if you thought of the distance idea first, then I would say solve the distance idea. If you think of the slope idea first, then go ahead and solve it with the slope idea. So we'll do both, just so that you can see that. If we were doing the slope idea, A to B, the direction from A to B, well, we've got some origin somewhere here. In order to go from A to B, you'd have to go negative A plus B. A is 2, negative 1, 1. B is 3, 2, negative 1. So A to B, if we put those together, will be 1, 4, negative 2. Now in 3 dimensions, what this means as a slope is the slope of our 3-dimensional line here, or a line in 3 dimensions, is that you're going to go 1 in the x direction, 4 in the y direction, and negative 2 in the z direction. Unless I've added something. Oh yeah, I added something up wrong. This should be 3, right? 1, 3, negative 2. Is that better? Good. So the slope of this line means that we're going 1 in the x direction, 3 in the y direction, and negative 2 in the z direction. So you had slope in 2 dimensions. You had rise over run. Okay. Now we'd have to come up with a new fancy slope thing, maybe like a fraction and a fraction, I don't know, x over y over z. I kind of like the z as my rise. I don't know, what could we call these both as runs, and one of them is like run x and run y. So runx runny rise has a nice ring to it, as the slopes in 3 dimension. I don't know. We would have to invent something. Well, and chances are if we look it up, someone probably has a proper terminology already decided for 3-dimensional slopes. But that's the idea. Now, if we go from B to C, well, we would go negative B, go back from B to O, and then go to C. Negative B would be negative 3, 2, negative 1, plus, and C is 6, 11, negative 7. Putting those together, we get 3, 9, negative 6. And what we need to notice is that I could factor a 3 out of here, and I get 1, 3, negative 2. Meaning that these ones are going in the same direction, and if they're going in the same direction, they would have to be a straight line. All you're doing when you're going from B to C is going 3 times further along that direction. So the slopes idea is just showing, am I going in the same direction? If I am, Perfect. The reason this is a lot shorter than the distance one is because in the distance one, you would have to find these same vectors. You would have to find a to b, which we did already, and we figured out a to b was 1, 3, negative 2. You would have to figure out b to c, which we did already, 3, 9, and negative 6. And you would also have to figure out a to c, which you could do in the same method. Just to save us some time, I'm going to tell you that it is 4, 12, negative 8. And then you would find the length of each of these. So a to b will be the square root of 1 squared plus 3 squared plus negative 2 squared. And if we simplify that all out, we're going to get 1 plus 9 plus 4, which is a square root of 14. If you're okay with me doing some quick mental math here, you could do the same thing with b to c. You would find out that b to c is the square root of 126. And if you did the same thing for a to c, you would find out that the square root of 224. Simplifying these radicals will tell us that the square root of 126, because you can divide that by 9, it's 9 times 14, means that this is 3 root 14. And simplifying a to c, you'd find that that is 4 root 14. So is a to b plus b to c the same length as going from b to c? It is, because both of them will be 4 root 14. So for a question like this, simplifying these vectors, you could draw out some points, A, B, C, D, E, and say, well, where would I end up? If I started from A to B and went from A to B, and then I went from B to C, then I went from D to E, and finally went from C to D, do they all fit together? Yes. The order doesn't matter. In fact, it would probably be a lot easier if these two were switched, right? Because then I would go from A to B, B to C, C to D, and then D to E. Where did I start? I started at A. Where did I end up? I ended up at E. So this whole thing is going to equal A to E. If you wanted to do it in smaller chunks, A to B plus B to C is the same as going from A to C. Then I'll just change the order here. And A to C plus C to D is the same as going from A to D. And then A to D plus D to E is the same as going from A to E. In part B, we've got a bunch of different things happening here. We've got 2 A to B's, 4 A to C's, 4 B to A's, 6 C to D's, 2 D to A's, and 2 D to C's. does it make sense that my b to a's are the same as negative 4a to b's? And my c to d's and my d to c's, I could, oops, my 2d to c's, I could make negative 2c to d's. So now I rewrote this one and this one. I rewrote this one and this one. I still have 4 a to c's and 2 d to a's.
Today has been officially canceled, so we will have classes as normal this afternoon. That is the bad news. The good news is, this week is Pride Week, and to celebrate Pride Week, the GSA is giving away rainbow ice cream in the front foyer. The Student Council is also giving away Sunday cups, and it's one or the other. And Student Council is also at a very extremely reasonable price, having pizza available in the cafeteria. See you at lunch.
So I put the ones that are the same together. And now this one became this, and this became that. Can you see that you could put these two together? If you're going 4a to c and then 4c to d, you could basically factor that 4 out, and that's going from a to c and then c to d. These two together will be like going from 4a to d. Can you also see that I could put these together? Going from d to a. Oh no, those aren't matched up. But if I can change it to, yeah. So I'll put those, so I've got minus 2ab still here, plus 4ads, and now I'm going to change this one to minus 2ads, because then these two are similar. And if I put those together, I have minus 2ab's plus 2 ADs. If I change this one back to positive, so you sort of see that it's important that if you're adding vectors, that the ending vector of one needs to be the starting vector of another one. So if I'm going from B to A and then from A to D, this will be the same as going 2 from B to D.